So in this lecture, we will define some special matrices, namely diagonal matrices, triangular matrices, and symmetric matrices. So these matrices have special properties that work only on them. So let us start with the diagonal matrix. So a diagonal matrix is a square matrix in which all the entries that are not in the main diagonal are zero. So, for example, here we have a 2 by 2 diagonal matrix, 4 by 4 diagonal matrix, and a 3 by 3 diagonal matrix. So, as you can observe, this is the diagonal for the 2 by 2 matrix, and notice that if the entries are not in the diagonal, they are all zero. Okay. Similarly, for the 4 by 4 matrix, this is the diagonal here. And all other entries that are not in this diagonal, they are all zero. And of course, the zero matrix trivially satisfies the condition for the diagonal matrix. Next, we define what we call triangular matrices. So a square matrix in which all the entries above the main diagonal are zero is called lower triangular. So we will see why they are called triangular later. A square matrix in which all the entries below the main diagonal are zero is called an upper triangular. And whether you are or you have a lower triangular or an upper triangular, we'll just call them the triangular matrices. So as I have mentioned, we will see why they are triangular and in particular why they are called lower and why they are called upper triangular matrices. So for example, we have these 2 by 2, 4 by 4, and 3 by 3 matrices. And in here, for this guy, I can draw this triangle here. Okay, I can draw this triangle here. So for here, we can draw this triangle in here. And notice that this is a triangle, okay, which is above or on the upper part of the matrix. So this is an upper triangular matrix. But notice, this is the diagonal, okay, of this 2 by 2 matrix, and all the entries below that diagonal, which is just a single entry in here, okay, is zero. For this 4 by 4 matrix, this is the diagonal that we have, okay? And all the entries above that diagonal, okay, they are all zero. But if we will draw the triangle, okay, this is the triangle that we are talking about, and that's why this matrix is called a lower triangular matrix. And for this 3 by 3 matrix in here, so again, we draw this triangle in here. So this is a lower triangular, but it has this condition, of course. This is the diagonal, and all the entries above the diagonal are zero. So this is a lower triangular matrix. Finally, we define what we call the symmetric matrix. Okay, so a square matrix A is said to be symmetric if the transpose of A is equal to A. And we also define what we call a skew symmetric. So a skew symmetric matrix A or a square matrix A is said to be skew symmetric if the transpose of A equals negative A. So the difference between the two, for the symmetric, the transpose is equal to A itself, while for the skew symmetric, the transpose is equal to the negative of the matrix. So here are some examples of symmetric matrices and skew symmetric matrices. So you can verify that if you get the transpose of this 2 by 2 matrix here, you will get the same matrix. Similarly, for this 4 by 4 matrix, if you get the transpose, you will get the same matrix in here. And in here, if you get the transpose of this matrix, you will still get the same matrix. But a good observation that we can make on skew symmetric matrices is that the ith row of the matrix is the same as the ith column of the same matrix. So for example, if we are looking at the first row of this 4 by 4 matrix, it is the same as the first column of this matrix. If we look at the third column of this matrix, this is the same as the third row of the matrix, and etc. etc. As for the skew symmetric matrices, so again, you may verify that if you get the transpose of this matrix and you also get the negative of this matrix, then they are equal. Similarly for this, if you get the transpose of this matrix and the negative of this matrix, they are equal. One good property of the skew symmetric matrices is that the entries on the diagonal of skew symmetric matrices are zero. So you can actually prove that this is always the case for skew symmetric matrices. Now let us talk about some properties that these new or special matrices have. First, a diagonal matrix is said to be invertible if and only if all of its diagonal entries are non-zero. So of course, the diagonal matrix, it only has um, possibly non-zero on the diagonal. But if all of the entries are actually non-zero, all of them are non-zero on the diagonal, then the matrix is invertible. So moreover, if we denote by capital D this diagonal matrix with diagonal entries D1, D2 until Dn, okay, and we assume that D1, D2 until Dn are non-zero, then according to this statement, this matrix D is invertible. And furthermore, the inverse of this matrix D is obtained by getting the reciprocals of each of diagonal entry. Okay, so for example, this is our matrix D, the diagonal matrix D. We get D inverse. Okay, so the first diagonal entry of the matrix D is non-zero. We get the reciprocal of that, which is 1 over D1. Okay, the second the second entry of the diagonal matrix D, okay, it's D2, again non-zero. So in the inverse, we get the reciprocal 1 over D2 and so on and so forth until the last entry of the diagonal matrix D, it's Dn. So in the inverse, we have 1 over Dn. And again, all the other entries are 0 for the diagonal matrix. Okay. Another remark in here, say we still have the diagonal matrix D with diagonal entries D1, D2 until Dn, not necessarily non-zero, okay? Then for any positive integer k, the power D to the k is the diagonal matrix whose diagonal entries are just to the kth power of the diagonal entries of the matrix D. So for the matrix D, diagonal entry D1. In the matrix D to the K, the diagonal entry is D1 to the K. For the second diagonal entry of the matrix D, okay, the second entry for D to the K, it's D2 to the K, and etc. until Dn to the K. Okay. Now, suppose A is an M by N matrix. Okay. If D is an n by n diagonal matrix, then the product AD is the matrix obtained by multiplying successive columns of A by the successive diagonal entries of D. So notice our A here is an M by N matrix, and the diagonal matrix is an N by N diagonal matrix. So we can only multiply D on the right of A. So we have this AD. Okay? Now, if the diagonal matrix is M by M, okay, then we can only multiply this diagonal matrix D on the left of A. So the product dA, it's the matrix obtained by multiplying the successive rows of A by the successive diagonal entries of D. So this particular remark, it's very helpful because we don't need to multiply entry by entry or row times column if we have this. So we only need to multiply successive columns by the successive diagonal entries of D if we want the product AD, or the successive rows of A multiplied to the successive diagonal entries of D if we want the product dA. Of course, assuming that they can be multiplied in this way. So to see this, let us consider this example. So this is our matrix A, this is our matrix B, and this is our diagonal matrix D. On the first one, we want to find dA. So the diagonal matrix is multiplied on the left of A. Okay. If we go to the remark, we are looking at remark 3B. So this means we will multiply successive rows of A by the successive diagonal entries of D. So what does this mean? For the matrix A, we have this row 1, okay? This row 1 in here, we will multiply this to the first entry in the diagonal matrix. So we will multiply this row 1 here to this entry of the diagonal matrix D. For second row of A, for the second row of A, so we have this second row here. So for the first row of A, this first row here, okay, we multiply this to the first entry of the diagonal matrix D. The second row of A, this will be multiplied to the second entry of the diagonal matrix D, and the third row of A will be multiplied to the third entry of the diagonal matrix D. Therefore, this dA here, this is simply equal to the matrix. So we just multiply this first row to the first entry here. So we will get negative 2, negative 4, 2, and negative 4 for the first row. For the second row, we multiply the second row to the second diagonal entry here. So we will get 0, 9, negative 15, and then 6. Okay. And lastly, the third row, this will be multiplied to the third entry in here. So we will get negative 4, negative 4, 16, and then 12. So this is the product dA. So again, you don't have to multiply out entry by entry to obtain this product. Okay. For the second product here, you have BD. So this time, the diagonal matrix D is multiplied on the right of the matrix B. Okay. So if we go back to this remark, we are now going to look at remark 3a. So for this, the remark 3a states that the successive columns of A here is multiplied to the successive diagonal entries of D if we want the product AD in here. So in this case, in this particular example, we will multiply the following. So for this first diagonal entry D, okay, this is multiplied to the first column of B. For the second diagonal entry 3, this is multiplied to the second column of B. And then the third diagonal entry here 4, we will be multiplying that to the third uh, column of B, which means the product, okay, the product BD can now be calculated, which means the product BD can now be calculated as follows. So the first column here will be multiplied to the first entry in here. So we will have -2, -10, +2, and then -4. The second column here multiplied to second entry here. So we get 6, 6, 9, 6. Okay. And then the third column there is multiplied to the third entry in here. So we get 8, 24, -8, and then 4. So this is the product BD. And again, we simply do this technique here, and we don't have to multiply term by term. Okay? Now, let us consider this diagonal matrix D. We want to find D cube and the T inverse. For the D cube, again, all we need to do is to cube all the entries, the corresponding diagonal entries. Okay? So, -2 cube, this is -8. 3 cube, this is 27. And then 4 cube, this is 64. And the rest of the entries, they are just zeros. So this is the cube. And for the inverse, so notice that all the diagonal entries here are non-zero. So this has an inverse. And the inverse can be obtained by writing the corresponding diagonal entries of D, okay, using the reciprocals. So 2 reciprocal is -1/2. 3 reciprocal is 1/3. Then 4 reciprocal is 1/4. And then again, the rest are just 0. So this is the inverse of the diagonal matrix D. Okay? Now, some properties for triangular matrices. The transpose of a lower triangular matrix is an upper triangular matrix. And the transpose of an upper triangular matrix is a lower triangular matrix. So this is intuitive in a sense that for lower triangular matrices, all the zeros are above the diagonal entries. Okay? And if you get the transpose of that lower triangular matrix, all those zeros will go below the diagonal of the matrix. And therefore, you will get an upper triangular matrix. And similarly, for the upper triangular matrix, you have all the zeros below the diagonal. If you get the transpose, they will go to above the diagonal. So it becomes lower triangular matrix. Now, the product of lower triangular matrices is lower triangular, and the product of upper triangular matrices is upper triangular. It means that the properties are retained if you are multiplying the same triangular type of matrices. If you multiplied upper triangular with lower triangular, we don't know what will happen. It could be any matrix. Okay, it could be lower triangular also, it could be upper triangular, but it could be anything. Okay. A triangular matrix is invertible if and only if its diagonal entries are all non-zero. So this is the same as the diagonal matrices. So for triangular matrix, invertible if and only if the diagonal entries are all non-zero. And later we will see a formula for the what we call determinant of the triangular uh, matrices. Okay. And the inverse of an invertible lower triangular matrix is also lower triangular. And the inverse of an invertible upper triangular matrix is upper triangular. So again, the triangular type will be retained if you just get the inverse. So for example, let us consider this matrix A, which is upper triangular. Matrix B is also upper triangular. Matrix C, it's lower triangular. So let's find the product, A times B, okay? And then let us also get the product A times C. So notice, A times B, upper triangular times upper triangular, so we expect another upper triangular in here. So let us write out that those matrices and the product. So 1, 2, -1, 0, 3, 5, 0, 0, 6. Okay, and for the AB, we get uh, and 0, 0, 6. 0, 0, 6. Okay, and then for the matrix B, we have 1, 2, 2, 0, 2, 6, and 0, 0, -2. Okay, so if we multiply them, let us see what we'll get. So we have first row times first column. So 1 times 1, that's 1. Okay, and then 2 times 0, that's 0. -1 times 0, that's 0. So we'll just have 1 in here. First row, second column, 1 times 2, that's 2, plus 2 times 2, that's 4, and then -1 times 0, that's 0. And then first row times third column, we will have 1 times 2, that's 2, plus 2 times 6, that's 12, plus -1 times -2, that's 2 again. Okay? Then for this entry, so second row, first column, we have 4 times 0, 0 times 1, that's equal to 0, 3 times 0, that's 0, 5 times 0, that's 0. So this is 0, which is to be expected, okay? And actually, we expect that this is also 0 in here, and the entry in here is also 0. So let us try to verify that one. And then let us now write the other entries in this, and this. So second row, second column, we have 0 times 2, that's 0, 3 times 2, that's 6 in here, then 5 times 0, that's 0. So in here, we have 0 times 2, that's again 0. 3 times 6, that's 18. And then 5 times wait, so let me check this. This is -5 in here, okay? And if that is -5, yeah. So it's fine. So now negative 5 times 2, that's positive 10. So plus 10. Okay. And finally, this entry here, third row, third column, we have 0 times 2, that's 0, 0 times 6, that's 0, 6 times negative 2, that's negative 12. Okay, and we close this. So simplifying, if we just simplify this, okay, then we will get the matrix 1 and then 6 in here, this is 16 in here, and then you have 0, 6, and then 28, and then 0, 0, negative 12. So again, this is upper triangular. Okay, let us do the other product in here. Okay, we want to find AC. So let us write AC here. So 1, 2, negative 1, 0, 3, negative 5, 0, 0, 6. And then for C, we have negative 2, 0, 0, 1, 0, 0, and then 1, 2, 4. Okay. So if we multiply this, okay, 1 times negative 2, that's negative 2. 2 times 1, that's plus 2. Negative 1 times 1, so minus 1. For the entry in here, first column, first row, second column, we have 1 times 0, that's 0, 2 times 0, that's again 0, negative 1 times positive 2, that's negative 2. So notice this is no longer 0, this cannot be lower triangular. If we get the entry in here, so second row, second row, first column, okay? You have 0 times negative 2, that's 0. 3 times 1, that's 3. Negative 5 times 1, that's negative 5. And 3 minus 5, that's negative 2, which is again non-zero. So this cannot be upper triangular. So it's just another matrix, as I have mentioned earlier. So anyway, let us just continue multiplying these stuffs. So 1 times 0, that's 0. 2 times 0, that's again 0. Negative 1 times 4, that's negative 4 in here. 0. So second row, second column, and then third column. So 0 times 0, that's 0. 3 times 0, that's 0. Negative 5 times 2, that's negative 10. And then for the third column in here, 0 times 0, that's 0. 3 times 0, that's again 0. Negative 5 times 4, that's negative 20. And finally, for the last row of the product, AC, so 0 times 0, 0 times negative 2, that's 0. 0 times 2, 0 times 1, that's 0. 6 times 1, that's 6. And in fact, all we need to do is to multiply that 6 on this last row here. So you have 6 and then 12 here, verify that, and then 24 in here. So if we just write the final answer in here, we have negative 1, negative 2, negative 4, negative 2, negative 10, negative 20. And then finally, you have 6, 12, 24. So this is the product AC. You can try the product BC and just try to get what matrix would that be, or it's just another general matrix again. Okay. Next, in here, is A invertible? If yes, find the inverse. So this is a triangular matrix. the diagonal entries are all non-zero, by the remark earlier, A must be invertible. So the answer will be yes. So if yes, find the inverse. We will try to find the inverse later. So is A invertible? Look at the matrix A here. We have a triangular matrix and the diagonal entries are all non-zero. So according to the remark earlier, the answer here is yes. And then we'll find the inverse later. Is B invertible? Again, triangular matrix. The diagonal entries are non-zero. Okay? So according to the remark, the answer here will be yes. If yes, find the inverse. So I will leave you for you to practice to find the inverse of the matrix B. And then finally, is C invertible? This is a triangular matrix, but one of the entries in the diagonal, particularly this middle part here, it's 0. So according to the remark earlier, the answer here would be no. Okay? So, to find the inverse of A, to find the inverse of A, we use the inversion algorithm. Okay, find inverse of A. So to find the inverse of A, we use the inversion algorithm. So how do we do that? We first copy the matrix A. Let us do that. 1, 2, negative 1, 0, 3, negative 5, and 0, 0, 6. And then we augment. We augment the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we will find the reduced row echelon form of this new matrix in here. So to find A inverse, we use inversion algorithm. And to do that, we copy the matrix A, 1, 2, negative 1, 0, 3, negative 5, 0, 0, 6. And then we augment the identity matrix. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. And then once we augment the matrix, we will find the reduced row echelon form of this. And the right-hand side of this 3 by 6 matrix will be the inverse of A. So first, let us remove all the things. We want to make this one and we want to make this one also. And then these three guys in here, we want them to be zeros. So in order to do that, let us start with dividing row 3 by 1, multiply row 3 by 1 over 6. So we divide row 3 by 6. And then row 2, we divide it by 3. Okay? We divide that by 3. So let us just adjust this guy. So what do we get? So row 1, we did not do anything. Row 1, we did not do anything. So we'll just have to copy that. 1, 2, negative 1. Okay, and then we augment here. 1, 0, 0. And then row 2, we divide it by 3. So we will get 0, 1, negative 5 over 6. And then, oops, sorry, negative 5 over 3. and then we have 0, 1 over 3, and then 0. And then for row 3, we divide by 6. So this will be 0, 0, 1, and then 0, 0, 1 over 6. Okay? And then after this, what do? We want to remove this here. We want to make this 0 and we want to make this 0. And in order to do this, okay, in order to do this, we what? We add row 2 plus 5 thirds row 3. Okay. And then for the first row, we just add row 1 plus row 3. And with that, what are we getting? So for row 1, we add row 1 plus row 3. So 1 plus 0, that's still 1. 2 plus 0, that's still 2. Negative 1 plus 1, that becomes now 0. On the right side, we have 1 plus 0, that's still 1. 0 plus 0, that's still 0. And then 0 plus 1 over 6, that's 1 over 6 in here. Okay. Next, for the second row, we have row 2 plus 5 thirds row 3, so 0 plus 0, that is 0 in here. 1 plus 0, that's still 1. Here you got negative 5 thirds plus 5 thirds, so this becomes 0. And then 0 plus 0, that's 0. 1 third plus 0, that's 1 third. And then 0 plus 5 thirds times 1 over 6, this becomes 5 over 18. 5 over 18. And finally, the third row, we just copy it. So 0, 0, 1, 0, 0, 1 over 6, 0, 0, 1 over 6. Okay? And then finally, we want this to be 0. So what we can do is to add row 1 minus 2 row 2. So for this step now, we will have 1 minus 0, that's still 1. 2 minus 2, that becomes 0. Then 0 minus 0, that is 0. Then we augment. We have 1 minus 0, that's 1. 0 minus 2 over 3. Okay? So that becomes negative 2 thirds. Let me write it this way. And then 1 over 6 minus 10 over 18. Let me just write this. Here, 1 over 6 minus 10 over 18. Okay? Then for the second and third rows, we just copy them. So 0, 1, 0, 0 here, 1 third, and then 5 over 18. And the third row, it's 0, 0, 1, and 0, 0, 1 over 6. Okay? So in here, this part here is your inverse of the matrix A. Therefore, let me just write the final conclusion in here. A inverse equals, so A inverse is 0, negative 2 thirds. 1, 6 minus 10 over 18, that's minus 7 over 18. try to verify that one. Then you have 0, 1/3, 5/18, and then you have 0, 0, 1/6. Okay, so if all the arithmetic are correct, this will be the inverse of, sorry, the first entry here, it's 1. Okay, I wrote 0. So again, if everything is correct, the inverse of A here is given by this matrix. And notice, this is upper triangular, the inverse is also upper triangular. Okay? Now let us look at these theorems. If A and B are symmetric matrices with the same size, and if K is any scalar, okay, then the transpose of A is also symmetric. Why? Because again, by definition, a symmetric matrix, so let me write the definition above here. So A is symmetric if and only if A transpose equals A. So we are assuming A to be symmetric. So this means that this guy here satisfies this. Okay? A transpose is also symmetric. Why? Because A transpose, this is equal to A. Correct? So this is the proof of one. But A is symmetric. Therefore, this A is also equal to A transpose. So A transpose, if you transpose that, you still get A transpose. That's why A transpose is symmetric. Okay? Now, the sum A plus B and A minus B, they are both symmetric. So to prove that, again, you want to know A plus B transpose. But we already saw that if you add two matrices, square matrices, and you get, well, if you add matrices, you get the transpose of that. It's the same as adding the transpose only. So this guy here is straightforward. This is A transpose plus B transpose. But again, A and B are symmetric matrices. So A transpose, that's your A, plus B transpose, that's your B. So you have this sum transpose, it's equal to the sum. Therefore, you have A plus B, a symmetric matrix. Same is true with the minus. This is minus, this is minus, this is also minus. Okay? For number 3, you have the scalar product K times A. That's also symmetric. So again, you want to get the transpose of KA. But our formula for the transpose of scalar times A, it's just K times A transpose. And then again, A is symmetric. So A transpose, that's just A. So you have KA. So you have KA transpose, that's equal to KA. So KA is symmetric. Okay? Question on this? Okay. For our next theorem in here, the product of two symmetric matrices is symmetric if and only if the matrices commute. Okay? The product of two symmetric matrices is symmetric if and only if the matrices commute. So, what is this? You have A and B. Okay? You want AB. That's the product. Okay? Your A and B here, these are symmetric matrices. Okay? Symmetric matrices. You have a product AB. Okay? You have a product AB. You want AB transpose equals AB. So this means that AB, so this guy here means AB, the product AB is symmetric. Okay? So this is the first statement here. The product of two symmetric matrices is symmetric. The second statement is this guy. The matrices commute. The matrices commute means you have AB equals BA. So this means matrices commute. Okay? Okay? So what we want to prove here is that if you have, so you assume A and B to be symmetric matrices. Okay? If you prove, or if you assume this statement 1 is true, you need to show that statement 2 will also be true. Conversely, if you assume statement 2 is true, you need to prove statement 1 to be true. Okay? But we will do this in one shot. So let us prove this. Okay? Of course, you have let A, B be symmetric matrices. Okay? Then we have AB. Okay? This is equal to the transpose. Okay? This is equal to the transpose of B transpose A transpose. Okay? I think this is too fast for this. We start with AB, but A, that's equal to transpose, and your B, that's also equal to transpose. And then we bring the transpose out. Okay? We bring the transpose out. This is equal to, so if you bring the transpose out, you have to interchange the two guys here. You will have B transpose A transpose. Okay? And then A and B were symmetric matrices. Okay? A and B were symmetric matrices. You will have B A transpose. Okay? Okay? So far, so good. Now, let's do this. I think I have to separate the two statements now. If, so for one, or for two implies one, okay? We assume two to be true. We will prove one. So for this statement, if AB equals BA, meaning if the two matrices commute, okay? If the two matrices commute, then AB equals, from this statement here, that AB is equal to BA transpose, okay? But AB equals BA, so this is equal to AB transpose, okay? So the product AB is symmetric, okay? So there is a question here, why do A and B interchange? That's the property of commutativity, okay? That's the property of commutativity, okay? AB equals BA, then the two factors commute. That's the definition, or that's the property commutativity. So again, if we assume 2, we assume that AB equals BA, then from this computation, this BA here, we can move that, or we can rewrite that as AB. So AB transpose equals AB, and therefore AB is symmetric. Conversely, if we assume statement 1, okay, we want to show that AB equals BA, okay? One has AB according to the condition statement 1. This AB, it's equal to AB transpose. But AB transpose, if we calculate this is equal to B transpose A transpose. But B transpose, because B is symmetric, that's just B. And A transpose, since A is symmetric, that's just A. And this is what we need. and therefore the theorem is proved. Okay? Next theorem. If A is an invertible symmetric matrix, then A inverse is also symmetric. If A is an invertible symmetric matrix, then A inverse is also symmetric. Proof? Okay. We assume A to be an invertible symmetric matrix. Okay. So let A be an invertible symmetric matrix. Okay. Then we calculate A inverse transpose. Okay. We want to calculate A inverse transpose. But we've seen this in one of the properties, okay, in one of the theorems that we did, or at least I showed you before. You can interchange these two guys, the inverse and the transpose operator. This is the same as A transpose inverse. Okay? But then again, A is a symmetric matrix. Therefore, A transpose, it's just A. Okay? And therefore, we have now the desired conclusion. A inverse transpose, it's equal to A inverse. Therefore, A inverse is symmetric. A inverse is symmetric. Okay? Questions? Let's consider this. If A transpose A is equal to A, then A is symmetric and A equals A squared. Okay? So, proof? We want to show that A is symmetric. Okay? We want to show that A is symmetric. So, one has, you start with A, you want to get the transpose of this, and you want to show that the transpose of A is also A. That's your symmetric matrix definition. But then again, this A here, it's A transpose A, which means that this A here, we can replace it with A transpose A. And then you have the transpose because of this. And then we apply the property of transpose. This is just A transpose A transpose transpose. So you interchange the two guys and you get the transpose. So this guy here went to the other side. That's why you have your A transpose here. And then this A transpose here went to the other side. So this is your A transpose, and then you transpose that. And then the transpose of the transpose, that's just your original matrix. So here you have A transpose because of this. But this guy here, A transpose transpose, that's just A. And then here we go again. A transpose A transpose A, that's just A. So this is equal to A. Okay? Therefore, A is symmetric. A is symmetric. Okay? So we're done with this first part here. The second part, we need to show that A equals A squared. But that is straightforward. So furthermore, we have A from the given. A is equal to A transpose A. But for this guy here, for the A transpose here, we've already shown that A transpose, that's also equal to A. So this is just A, and therefore this is just A squared. So we have this part here. Okay? Questions? Next here, this will be the last example for this lecture. Now, a square matrix is said to be skew symmetric if A transpose equals negative A. So that's what we have defined earlier. So we want to prove that if A is an invertible skew symmetric matrix, then A inverse is also skew symmetric. So the proof will be similar to the other theorem that we proved earlier. Okay? So proof, we want to show A inverse transpose. This must be negative A. Okay? We need a negative. Sorry, A inverse transpose. This should be negative A transpose. Huh? No. We need to prove A inverse transpose. That should be equal to negative A inverse. That's correct. So we need to prove that A inverse transpose, that's equal to negative A inverse. And therefore, we have the skew symmetric property. But then again, this guy here, just like before, we can interchange the transpose and the inverse operator. So we have A transpose inverse. But A is skew symmetric. Therefore, this is just negative A. And then we have that inverse. But this negative here, it can go out. So we will have negative of A inverse. Okay? So let me just write it here. One has this. Therefore, that's what we need. A inverse is skew symmetric. Okay? And that's the end of the proof here.